Alright, welcome back to your favorite Fundamentals College Math class. We're going to look at linear regression. Now we've explored linear equations, right? Anything of the form y equals mx plus b, right? Where we got our slope right there, our y-intercept there. So we got a line of some sort, and of course if we have a positive slope, it'd be going up like and to the right. It's increasing with a positive slope. If it's going down to the right, we'd have a negative slope decreasing. If it's perfectly horizontal, slope is 0. And of course, if the slope is undefined, it'd be a vertical line, right? So if you're looking at this, let's say that we have here, we've got a graph. It's representing the relationship between the age of a vehicle, is the horizontal axis, in years, right? This is years. And its value. For a handful of vehicles here, all the same. We'll say they're all the same model, okay? So like this one maybe is like, I don't know, after 1.5 years, maybe it's worth 7,000 or whatever, right? 7,000 bucks. But anyways, it's got all this data. Can we write a linear equation? In other words, do these points all go through a line perfectly? You say, no, not perfectly, right? But is there a straight line that kind of models this? In other words, like a line of best fit, if you will. Maybe it's that red line, right? Of this scatter plot. By the way, a scatter plot is just a plot of all these points, right? But is there a line of best fit? Well, I did my best to write that red line that kind of models that, but there's a mathematical way to come up with that line of best fit, and that's called linear regression. And so we're going to let our graphing calculator do that for us. And what it does, just to give you kind of an idea of what it does, is it tries to minimize what's called your error, right? The sum of the error right there. See how there's a difference between that data point and the red line there? It's trying to minimize that as best it can when it does what is called a least squares regression line. Okay, so it makes the vertical distance from the data points as small as possible. Okay, so let's go ahead and see if we can't do this with our Desmos calculator. So if you want to open up Desmos.com, and let's go ahead and start plotting these points, 0, 196, 1, 192, and so on. Okay, so we open up Desmos.com, I click on the graphing calculator, and then I'm going to go ahead and take all these points right here, 0, 196, 1, 192, 2, and so on. So how you do that, how you plot those, is you go up here to the left plus arrow, click on that, a little plus in the upper left, and click on table. And our inputs are 0, 1, 2, 3, 4, and 5. The y values, and that's, by the way, that's time in weeks, and this is our weight. What we're doing is we're plotting data showing a person's body weight during whatever week they're in. So initially, at time 0, they start out at 196 pounds. After a week, they lost 4 pounds. Now they're at 192 pounds. Then if they're like me, they were feeling pretty good about life and ate a bunch of ice cream and went up in weight. And then they went down in weight, stayed at that weight, and then the 5th week, they dropped a few more pounds. So there's all our data points. Now, if you notice, I don't see these data points. I could go over here to the right and zoom out. It's kind of ugly. You know, they're all bunched right there. So what I'm going to do is I'm just going to change my window. So go up to the top right wrench. And I'm going to go from let me go from -1. You see my x values go up to 5. Let me go up to like 10. I'll go a little bit past that. Okay, up to 10. Now my y-axis, I'm going to go... Let me go like -10. And notice the y's go up to a maximum of about 196. So let me go up to I don't know, let's go 300. That'll give me a pretty good window. And then I'm going to click off my wrench there. So -1 to 10 on my x-axis, y -10 to 300. Again, that's coming from my x's and my y's on my window. So if you look at this, you can kind of tell this is kind of following a line. I could draw if I could draw. Unfortunately, I can't draw on this graph, but it's kind of following a line. So we're trying to find that line of best fit. We're going to use part B on this says use Desmos to find the regression equation. So what we're going to do is we're going to say right here on line 2, click down there below, go y1. So it's taking all my y1 data. And then I'm going to do, I think it's called a tilde, a little squiggly tilde. That's it's kind of next to my number 1 button on my keyboard. It's just to the left of that. It's like shift, that button. So you got a little tilde. You could probably pull the drop down menu and find that little tilde. And then I'm going to go mx1 plus b. And so what this does is it takes all your data and minimizes it, right? It creates this line of best fit, does a statistical process here, and gives you the m, your slope. Notice it's decreasing, so your slope is negative. See that -1.68571? And it gives you the y-intercept there, 195.38095. So we're going to go ahead and take the, we're going to write the equation of this. Note the m. M is -1.68571. Note the b right there. Unfortunately, I'm having a hard time putting that image on an image here, so my apologies. So y equals m -1.68571 plus the b that it gave me, which was 195.38095. Now we want this y, the output, to be in terms of weight and pounds, and we're going to also round this, to the nearest hundred. So -1.69 times 195.38. That's our regression equation right there. So again, we're making the graphing calculator do all that mathematics for us. It's doing quite a bit, by the way. I know it spits it out really fast, but there's a lot of good math that it's doing there. It's pretty awesome. All right, interpret the meaning of the vertical intercept. So when this was initially drawn, it was like this or whatever. Your vertical intercept right there, as far as the equation is concerned, that's your weight. That's the weight, 195.38 pounds at time being 0. So when you start, when you start the program, or before you start the program, that's your vertical intercept here, right? That point. Interpret the meaning of the slope. Well, our slope here, remember, this is our weight, this is our time in weeks. So the slope, what does that mean? Well, we know our slope is change in y over change in x, right? y2 minus y1 over x2 minus x1. In other words, here it's the change in your weight over the change in time. Well, what is our slope? It's -1.69. Now let me make that into a fraction. There's no denominator, so just put it over 1. So that means we're dropping 1.69 pounds. We're losing 1.69 pounds per week. That's what it means. We're losing -1.69 pounds per week on average, right? That's what the slope is telling us. And finally, it says use your regression equation. So let's go ahead and write our regression equation, -1.69t plus 195.38, to find our weight after 2.5 weeks. So we're just going to let t be 2.5. We'll go ahead and plug that in. So W equals -1.69 times 2.5 plus 195.38. And we punch that in, and we'll get 191.155. So our weight after 2.5 weeks is about 191 pounds, if I round to the nearest pound there. Let's do the same thing except for 6 weeks. So the weight after 6 weeks, negative 1.69. Now just multiply it by 6. Our weight after 6 weeks ends up being negative 1.69 times 6 plus, let's see, that's 185.24 pounds. So about 185 pounds after 6 weeks. And lastly, would it be reasonable to predict the weight in pounds after 100 weeks? Well, if you put 100 weeks in, let's think about this. If you're losing 1.69 pounds a week, right? Do you really want to do it for 100 weeks? Hopefully you're responding, you do not want to do that, because if you're losing 1.69 pounds a week, you don't want to do it for 100 weeks. You'd only be 26 pounds at the end of that time period. So no, not reasonable to lose that kind of weight for that long, right? To lose the weight for that long doesn't make any sense. All right, let's do another regression equation here. This time we've got a table giving a number of Christmas trees sold in millions in the U.S. from 2004 to 2011. So we're going to let 2004 be the initial year. So that's like t being 0. Notice it down here. So our XY table will be 0 in year 0. In 2004, there's 27.1 million Christmas trees sold. 2 years later, 2006, there's 28.6, and so on. So you'll have 0, 2, 4. 2010 is 6 years later. 2011 is 7 years later, right? That's going to be our data set. We're going to go ahead and pull up Desmos.com again. Let's go ahead and punch in and plot this scatter plot. Open the graphing calculator. So upper left, table right there. And we had 0, 2, 4, 6, and 7. Again, year 0 was 2004. And in 2004, there's 27.1 million Christmas trees sold, 28.6, 28.2, 27, 30.8. Make sure you're really careful when you're plotting these. And then notice again, it doesn't show us the scatter plot unless you kind of zoom out, but even then it's not the greatest. So let's do this window. Let's go from like -1 to 10 or so with our X. So I go upper right to the wrench. I'm going to go from like -1. Let's see how it looks. It's up to 10. That's pretty decent. Or maybe I'll go 15. Kind of push it over a little bit. My Y, I'll go, how about -5 up to, my biggest Y value is 30.8. So let's go up to about 40 or so. Or maybe, oops. What am I doing? Sorry. It's 15. There we go. My Y, what did I say? -5 up to about 40-ish. Click off. And there's a little bit better window, I guess you could say. You could always zoom in and zoom out as well. Desmos.com. So here's our scatter plot, right? Now, can you kind of see how it follows sort of a line? So we're going to have a line of best fit, so it's linear. So we're just going to go down here, click on number 2, and click Y1 tilde MX1 plus B. Now you got to have those subscript 1s on those because it's taking X1 data and Y1 data, right? From the data up above it, right? And now I'm going to note, see how my slope is 0.278659. It's got a positive slope. See how it's going up and to the right? It's increasing. So year to year, we're buying more Christmas trees, right, on average. So what that's saying. So let's go ahead and put that into our equation. They want that regression equation. So I'm going to note my M and my B. And I'm going to go ahead and write it down. Oops. Here, part, whatever part that is. Or A, it was determine the regression equation. All right, so the regression was y equals, my M was 0.278659. My B was 27.2811. Now this is Christmas tree, so I'm going to do a capital C here in terms of time t, and I'm going to go ahead and round this to the nearest thousandth, so 0.279 t. 27.281. Again, I'll round it to the nearest thousandth on this one. So here's my equation. Interpret the meaning of the vertical intercept. So that's our vertical intercept, right? So in year 0, which is 2004, there were, according to the regression equation at least, there were approximately 27.281 million Christmas trees sold. Now, I do want you to know, in all reality, the data said we actually had 27.1 million sold, right? Remember, the regression equation is just an approximation. It's doing its best to model the data. It's not perfect. Identify the slope of the regression equation. Well, our slope here is at 0.279. All right, so we had, this is T years, this is number of Christmas trees. Slope is change in the number of Christmas trees over change in time. And it's 0.279. Now this is in millions per 1 year, right? There's a 1 on the bottom of that. So in other words, there were 0.279 million, so that would be, if you multiply that by a million, that's 279,000 trees are sold per year, more on average, more per year since the year 2004. So each year we're selling 279,000 more Christmas trees, right? According to this data, at least. And then let's go ahead and predict it. So for the year 2013, well, 2013 is how many years since 2004? Yeah, good. Oops. What just happened? I don't know what I did. So 2013 is 9 years later from 2004. 2013 minus 2004 is 9 years later. So let's plug 9 in. 0.279 times 9 plus 27.281. And we'll get 29.792 million is how many were sold in the year 2013. And then should you predict it for in the year 2030? Well, this is a discussion here. Well, should we predict it for the year 2030? I want to go back to this data. Notice the data is from 2004 to 2011. It's saying, should you use it to, the term is extrapolate, to predict outside your data set? Well, frankly, it's probably going to be a little unlikely that it's very accurate because you're extrapolating outside the data set. So we're going to say no on that. If you're interpolating, if you're predicting within the data set, it really is more likely to be accurate. Again, stereotypically. No, the original data was from 2004 to 2011. Extrapolating, in other words, predicting outside the data points, at least that far, right? Out that far. probably unlikely to be accurate. Again, it's all contextual. Right, depends on what you're looking at. All right, we're going to move into what's called the linear correlation, or the correlation coefficient. So that R, when we run our data and we get the regression equation, it actually gives us an R value. Again, that's called the linear correlation, or the correlation coefficient. Okay, and what it does is it tells you how strong the strength and the direction that the relationship is. So it's kind of like, how good is it? How well of a predictor is it, or is it have a lot of error in that prediction, right? So R is representing a correlation. It's going to be a value between -1 and 1. If R's negative, we have a negative relationship between the variables, and if it's positive, we get a positive relationship between the variables. And then the closer you are to 1, the stronger it is, or the closer you are, if it's negative to -1, the stronger the relationship is. I think it's best probably seen right here. Here's a bunch of scatter plots. And, if we were drawing the line of best fit, it might be something like that. You see how there's not a whole lot of error between the data points and the line? There's not a whole lot of distance between there. That's because it's got a pretty strong, close to 1 R value, correlation coefficient. It's pretty close to 1. It's a pretty strong predictor. So we would say this as a strong positive relationship. Positive relationship meaning, like maybe this is, as I age, my weight goes up, right? It's increasing or whatever. You got a positive relationship. Now this next one, see how it's like, I can't even tell if that's like a line or what, man. This is just kind of a mess. It's just not very close to the data point, right? There's a lot of error there. That's why that R value is not very close to 1. Okay, and so you say it's negative, it's closer to 0, so this has a very weak, negative linear relationship. This other one was a strong, because it was close to 1, strong positive linear relationship, right? This next one, I've got an R that's -0.88. R is negative. See, that's pretty close to -1, right? And you can tell it doesn't have that whole lot of error. So this is pretty close to -1. We got another strong, but in this case, though, it's negative, strong negative linear relationship there. And then this one, this R of 0.58, that's kind of a so-so. You're kind of in the middle between 0 and 1. As far as the R value is concerned. So you say there it is positive. I'd call this moderate linear relationship. 0.58 is just not very close to 1, right? You had a question about like, what would a negative relationship look like? Time going on, the value of your car is going down, right? So at year 0, maybe it's worth this much, but a year later, it's worth 2,000 less or whatever, right? As time goes on, I got a negative relationship there. The value of my car is going down, right? Negative relationship, and frankly, a pretty strong negative relationship in terms of potential car value. All right, let's go back to our weight loss situation when we were on the diet program. It says use your graphing calculator to find the correlation. So I'm going to pull that up again on my Desmos. I did not delete that. So if you need to, punch the data back in. And it's this one right here. Now notice this R value right there. See how the R is pretty dang close to -1, -0.9354 down there? Negative 0.9354. Let me make a note of that. So my correlation coefficient is negative 0.9354. Let's round it to the nearest hundredth. Negative 0.94. So we have a strong, it's pretty close to negative 1. We have a strong negative linear relationship right there. Wasn't a whole lot of error between the line and the data points. Okay. Notice this r squared right there. We're not in a stats class or anything, but I want you to make a note of that. That r squared 0.875. Before I do part B, that r squared 0.875. Now, we don't really cover that concept in here, though, but to give you a brief overview, that's called the coefficient of determination. Your range is from 0 to 1, or in other words, 0 to 100%. It gives the percentage of variation of y in terms of as explained by x variables. So like, for example, here it's saying 87.5% of the points fall within the regression line. It's kind of like saying that's how accurate it is, kind of deal, right? So just an FYI, that's your variation, but I'm going to erase that for now. All right, let's get back to interpret the meaning. Oh, I did that. That's the strong negative linear relationship part, right? All right, let's go to our next one that we had, the Christmas trees. And let's look back and let's note the R that we got on that one. Pull up our decimals again. Let's see what we had for our R. Right here, see the R is 0.5185. 0.5185. R equals 0.5185. So not very close to 1, it's kind of between 0 and 1. So we're going to say this is a moderate. It is a positive value. Positive, but pretty moderate linear relationship between time in years since 2004 and number of Christmas trees sold in the U.S. So moderate positive linear relationship. And that's it for our correlation coefficient. Thanks so much for watching. We'll pick up next time.